Hello and welcome. It's good to have you here in this quiet corner of the night. Some nights the sky feels fuller than it should, stars scattered like forgotten promises, each one burning with a certainty we can only admire from down here. But what if I told you that between those points of light in the spaces where darkness pools deepest, there are things that almost became stars, things that dreamed of fire but never quite caught the spark? Things that glow softly alone, waiting in the cold. Tonight we're going to drift into one of the universe's most beautiful mysteries. Not the brightest stars, not the loudest explosions, but the quiet ones. The ones that tried to wake up but couldn't. The ones we call brown dwarfs. Before we begin, if you find comfort in these quiet journeys through the cosmos, you might like to stay a while. You can gently tap the like button. Subscribe if you'd like more stories, told softly, and ring the little bell not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Imagine you're floating in the darkness between stars. Not the empty darkness of a room at night, but the kind of darkness that stretches for light years, cold and patient. Most of what we think of as space, the space between the bright things, isn't really empty. It's filled with dust, with gas, with the raw ingredients of stars waiting to happen. And sometimes in those stellar nurseries where new stars are born, something goes wrong. Or maybe it goes right in a different way. A cloud of gas begins to collapse under its own weight. Gravity pulls it inward, tighter and tighter. The center gets hot. Atoms press together. In most cases, if there's enough mass, if the cloud gathered enough material, something extraordinary happens. The core reaches about 10 million degrees, and hydrogen atoms begin to fuse into helium. A star is born, a furnace that will burn for billions of years, sending light across the galaxy. But what if there isn't quite enough? What if the cloud gathered 90% of what it needed, or 80 or 70? What if it pulled itself together, compressed, heated, but stopped just short of that critical threshold? The core warms, yes. It glows faintly, but the fire never catches. Fusion never begins, not the kind that makes a true star. This is how brown dwarfs are born, not in failure, but in the space between becoming. They are objects too massive to be planets, too small to be stars. They exist in the in-between, glowing, with the memory of heat, slowly cooling across billions of years. The first person to imagine such a thing was an astrophysicist named Shiv Kumar. The year was 1963. Scientists had been studying stars for centuries, mapping their life cycles, understanding how they formed and died. But Kumar asked a different question. He asked, what if a star never fully forms? What if it stops halfway? He calculated the minimum mass needed for hydrogen fusion, the nuclear fire that powers stars like our sun. That mass turned out to be about 8% the mass of the sun, roughly 80 times the mass of Jupiter. Anything below that, Kumar realized, would collapse, heat up, but never ignite. He called these objects black dwarfs at the time, though the name would later change. For 30 years, brown dwarfs were theoretical. Scientists believed they existed, the math said they should, but no one had ever seen one. And that makes sense, doesn't it? If they don't burn like stars, if they only glow faintly in infrared, how do you find them? How do you see something that barely whispers light into the void? The universe is full of things we can't see. Dark matter, black holes, the far side of distant moons. But brown dwarfs are different. They're not invisible because they're exotic or strange. They're invisible because they're subtle. They're the soft exhale of a star that never took its first breath. And here's something worth sitting with for a moment. We spend so much time looking at the brightest things, the supernovae, the quasars, the blazing cores of galaxies. But what about the things that almost were? What about the potential that never quite flowered? There's something achingly human about that, isn't there? The dream that didn't come true, the ambition that fell just short, the light that wanted to shine but couldn't. Brown dwarfs don't apologize for what they're not. They exist quietly cooling in the dark, glowing infrared against the black. They are what they are, and maybe that's enough. Scientists estimate there could be billions of brown dwarfs in our galaxy alone. Billions of these quiet in-between objects drifting through space unseen by most telescopes, unnoticed by most eyes. An invisible population outnumbering the stars, we can see filling the spaces we thought were empty. Think about that. Right now, scattered across the Milky Way, there are more brown dwarfs than we ever imagined. Some of them are young, still warm from their formation, glowing a deep red. Others are ancient, cooled down to temperatures barely warmer than a winter night on Earth. Some have storms raging across their surfaces, winds screaming at thousands of miles per hour. Others are calm, silent, alone. And here's the strange part. For most of human history, we didn't know they existed. We looked up at the night sky and saw stars, planets, the moon. We built stories around what we could see. But the brown dwarfs were always there in the margins, in the spaces between the constellations, glowing too faint for our eyes, waiting. It makes you wonder, doesn't it? What else is out there just beyond the edge of our vision? What other mysteries are hiding in plain sight, waiting for the right instrument, the right question, the right moment of curiosity? Brown dwarfs remind us that the universe doesn't owe us clarity. It doesn't arrange itself for our convenience. Some of the most profound things are the hardest to see. Some of the most beautiful stories are told in whispers, not shouts. And tonight we're listening. We're going to walk through the life of a brown dwarf, from birth to the slow, endless cooling that follows. We'll meet the scientists who hunted them for decades, the telescopes that finally glimpsed them, the strange weather patterns that swirl across their surfaces. We'll talk about the coldest brown dwarfs ever found, objects so dim they're nearly impossible to detect. We'll ask whether life could exist in their atmospheres, whether planets could orbit them, whether these failed stars might teach us something about the nature of existence itself. But we're not in a hurry. There's no need to rush. Brown dwarfs have been cooling for billions of years. They'll wait for us. So, settle in. Let your breathing slow. Let the weight of the day fall away. You don't need to understand everything. You don't need to remember every detail. Just rest and let curiosity do the listening. Because here's the truth, the quiet truth that sits at the heart of this story. Not everything that shines is a star. Not everything that burns is bright. Some things glow softly, steadily in the dark. Some things exist in the spaces we overlook, the gaps we don't think to check. And maybe that's where the real wonder lives. Not in the supernova, but in the ember. Not in the blaze, but in the slow, patient warmth of something that never needed to be more than it was. The universe is vast, yes. But it's also gentle. It makes room for the things that almost were. It holds space for the in-between. And so do we. So, let's begin this journey together, softly, slowly, into the heart of the stars that never fully awoke. Let's drift into the hidden corners of the cosmos, where brown dwarfs wait glowing, faintly reminding us that not all light needs to shout to be seen. The night is long and the stories are patient. We have time. The story of how a brown dwarf is born begins not with fire, but with falling. Imagine a cloud in space vast beyond comprehension, stretching for light years in every direction. It's made mostly of hydrogen, the simplest element, the most abundant thing in the universe. Mixed in are traces of helium, specks of dust, molecules of carbon monoxide drifting in the cold. The temperature hovers just a few degrees above absolute zero. Nothing moves quickly here. Time passes differently in the quiet between stars. But gravity is patient. Even in a cloud so diffuse that it barely exists, gravity is always working, pulling, tugging, drawing every atom toward every other atom. And sometimes maybe because a nearby star exploded, maybe because another cloud passed too close, a ripple moves through the gas, a disturbance, a compression, and the cloud begins to collapse. At first, the collapse is slow. Atoms drift inward, gathering at the center. The core grows denser. As more mass accumulates, gravity strengthens. The collapse accelerates. What took millions of years at the beginning now happens in thousands. The cloud fragments breaking into smaller pockets where stars will eventually form. Each pocket pulls in more gas, spinning faster as it shrinks, flattening into a disk. At the center of each disk, a protostar begins to glow. This is the beginning of every star. Our sun formed this way 4.5 billion years ago in a cloud much like the ones we see today, in places like the Orion Nebula. The process is well understood. Gas collapses, heats up. And if there's enough mass, the core temperature climbs until it reaches roughly 10 million Kelvin. At that point, hydrogen nuclei moving fast enough, press close enough, overcome their natural repulsion and fuse together. Helium is born. Energy floods outward. The star ignites. But brown dwarfs stop just short of that moment. They gather mass, yes. They collapse, heat up, glow. But they never cross the threshold. Research shows that the minimum mass required for sustained hydrogen fusion is about 0.08 solar masses, or roughly 80 times the mass of Jupiter. Anything below that, and the core simply doesn't get hot enough. The pressure isn't sufficient. Fusion doesn't begin. So what happens instead? The protostar keeps collapsing until the pressure from the material itself pushes back against gravity. It reaches a kind of equilibrium, a balance. The object is now as small as it's going to get, roughly the size of Jupiter, despite being dozens of times more massive. And it glows. Not from fusion, but from the heat of its own formation. The gravitational energy released during collapse gets converted into thermal energy. The brown dwarf radiates that warmth into space slowly, steadily over billions of years. Scientists suggest that brown dwarfs can burn deuterium, a heavier isotope of hydrogen, if they have enough mass. The threshold for deuterium fusion is much lower, around 13 Jupiter masses. Deuterium fuses at cooler temperatures a few million Kelvin instead of 10 million. So, for a brief period, perhaps a few million years, at the beginning of a brown dwarf's life, it does experience fusion. It burns through its deuterium, releases energy, and then the fuel runs out. The fusion stops, and the long cooling begins. It's worth pausing here to appreciate what didn't happen. The brown dwarf was so close. If it had gathered just a little more mass from the surrounding cloud, if the collapse had pulled in 10 or 20% more material, it would have crossed the line. It would have become a red dwarf, the smallest, faintest type of true star. Red dwarfs burn hydrogen for trillions of years, far longer than the current age of the universe. They're stable, patient, long-lived. But the brown dwarf missed that threshold. And so, instead of a trillion-year lifespan, it gets something different. It gets a slow fade, a gradual dimming. It starts out warm, glowing, and deep red, maybe even visible to the naked eye if you were close enough. Over millions of years, it cools. The red fades to infrared. After 1 billion years, it's cooler than a campfire. After 10 billion years, cooler than a summer day on Earth. It never stops cooling. It just gets fainter, quieter, harder to see. There's something poignant about that isn't there. The brown dwarf doesn't explode. It doesn't collapse into a neutron star or black hole. It doesn't go out in a blaze. It simply cools alone, glowing softer and softer against the dark. Like a coal pulled from a fire, left on a stone, still warm to the touch, but slowly, inevitably giving up its heat to the night. Now, here's where it gets interesting. For decades, scientists debated whether brown dwarfs were more like stars or more like planets. The answer, it turns out, is neither, and both. Brown dwarfs form the same way stars do, from collapsing clouds of gas. They're not built up piece by piece like planets, not assembled from dust and rock in a protoplanetary disk. They condense directly from the cloud, just like stars. So, in that sense, they're stellar objects. But they don't fuse hydrogen. They don't shine the way stars do. They cool over time like planets. Their atmospheres develop weather patterns, cloud storms. In many ways, they behave more like giant planets than like stars. Jupiter, for instance, radiates more heat than it receives from the sun. It's still cooling from its formation, just like a brown dwarf. The difference is one of degree, not kind. So, where do we draw the line? When does a brown dwarf become a planet? Scientists have settled on a somewhat arbitrary boundary. If an object forms from a collapsing cloud and has enough mass to fuse deuterium, it's a brown dwarf. If it forms in a disk around a star and never fuses anything, it's a planet. But nature doesn't care about our categories. Nature makes what it makes, and sometimes those objects sit right on the edge, defying easy labels. Consider this. There are objects called rogue planets worlds that formed in orbit around a star, but were later ejected, flung out into interstellar space by gravitational interactions. They wander the galaxy alone, no longer bound to any sun. Some of these rogue planets might be Jupiter-sized, even larger. Are they still planets? Or have they become something else? And then there are brown dwarfs that might have planets of their own, small rocky worlds orbiting in the faint warmth of a failed star. Are those planets? Do they count? What do you call a moon-sized object orbiting a brown dwarf that itself is barely larger than Jupiter? The universe is full of edge cases, objects that don't fit neatly into boxes. And brown dwarfs are perhaps the ultimate edge case, the misfit children of stellar nurseries, too big to be planets, too small to be stars, existing in the liminal space between categories. The first theoretical models of brown dwarfs, the ones Shiv Kumar developed in the 1960s, predicted they would be rare. Kumar thought they might form occasionally under special circumstances, but that most collapsing clouds would either form stars or disperse without forming anything. He was wrong about that. Later observations, once we had the technology to detect brown dwarfs, revealed they're far more common than anyone expected. Some estimates suggest there could be one brown dwarf for every few stars, maybe even more. They're not rare, they're ubiquitous. But why? Why does the universe make so many of these in-between objects? One possibility is that the process of star formation is messy. When a cloud collapses, it doesn't collapse uniformly. It fragments into pieces of different sizes. Some pieces are large enough to become stars. Others are smaller. The smallest pieces might become brown dwarfs. It's a natural outcome of the chaos of collapse, the turbulence of gas clouds jostling and compressing in the dark. Another possibility is that brown dwarfs form as companions to stars born in the same cloud orbiting each other. Many brown dwarfs have been found in binary systems, paired with either a star or another brown dwarf. Some scientists believe that interactions in these early systems, gravitational tugs and pulls, might prevent some objects from gathering enough mass to become stars. They're stunted in a sense by the presence of a larger sibling. But regardless of how they form, the result is the same. An object that almost made it. An object that carries the potential for stardom in its core, compressed and hot, but not quite hot enough. An ember that never became a flame. And here's the thing. We tend to think of failure as a negative, as something unfortunate, something to be avoided. But what if a brown dwarf isn't a failure? What if it's just a different kind of success? It exists. It formed, it glows, it has structure, atmosphere, maybe even weather. It's a complex, dynamic object, a world unto itself. It didn't need to become a star to matter. There's a lesson in that, maybe. Not everything needs to fulfill its supposed potential to be valuable. Not everything needs to burn bright to be beautiful. Some things just are quietly in the margins, and that's enough. The universe made room for brown dwarfs. Billions of them, scattered across every galaxy, drifting through the spaces between the bright points of light. They're part of the cosmic ecosystem, part of the web of matter and energy that makes up everything we see. They contribute to the gravitational landscape, influence the motion of nearby stars, possibly even host planets. They're not footnotes, they're chapters. So when we look out at the night sky, at the stars that shine so clearly, remember that between them in the darkness, there are other objects. Quiet ones. Objects that condensed from the same cloud, spun from the same matter, but took a different path. They're there glowing softly in infrared cooling, slowly across billions of years, patient and unhurried. They're the brown dwarfs, the stars that never fully awoke. And their story is just beginning. Because while we know how they're born, while we understand the physics of their formation, there's still so much we don't know. What happens to them over trillions of years? Do they ever stop cooling, or do they fade forever? Can they support life? Can they teach us something about the nature of matter, of energy, of existence itself? These are the questions we'll explore as we continue. But for now, just sit with the image. A cloud collapsing, a core heating, a moment of almost. A glow that persists softly in the dark. That's where brown dwarfs live. In the almost. In the in-between. And that's exactly where we're headed next. For 3 decades, brown dwarfs existed only in equations. They lived in the minds of theorists and computer simulations, in the careful calculations of physicists who believed the universe must make these objects, even if no one had ever seen one. 30 years is a long time to believe in something invisible. Long enough for doubt to creep in. Long enough to wonder if the theory was wrong, if the math had missed something fundamental, if brown dwarfs were just elegant ideas that nature had decided not to bother with. But the scientists kept looking. Because sometimes belief is enough. Sometimes you trust the equations, trust the logic, and you keep searching even when the darkness gives you nothing back. The problem was simple, brutal in its simplicity. Brown dwarfs are dim. Not just faint, but almost imperceptible. They don't burn hydrogen, so they don't shine with the steady light of stars. They only glow with leftover heat, and that heat radiates primarily in the infrared part of the spectrum, wavelengths our eyes can't see. To human vision, a brown dwarf is invisible. Even a telescope pointed directly at one would see nothing but empty space unless that telescope could detect infrared light. And for most of the 20th century, infrared astronomy was in its infancy. The technology existed barely, but it was crude. Infrared detectors had to be cooled to incredibly low temperatures to avoid being overwhelmed by their own heat. The atmosphere absorbed most infrared wavelengths before they could reach ground-based telescopes. Observing from space was expensive, complicated, rare. So, astronomers searched with the tools they had, which were not quite good enough. Year after year, they looked. And year after year, they found nothing. Imagine the frustration. You know something is out there. The physics demands it. But you can't see it, can't prove it, can't hold it up to the light and say, here, this is real. You start to wonder if you're chasing shadows, if you've spent your career on a wild hypothesis, if the universe is laughing at you quietly in the dark. Then, in the early 1990s, technology caught up with theory. New infrared detectors became available, more sensitive, more stable. Telescopes improved. Surveys began that could scan large portions of the sky in infrared wavelengths, cataloging everything that glowed no matter how faintly. And finally, after 3 decades of searching, brown dwarfs started to appear. The first confirmed brown dwarf was discovered in 1995. Its name was Tida 1, found in the Pleiades star cluster, that beautiful gathering of young stars visible to the naked eye on winter nights. The Pleiades cluster is relatively young, only about 100 million years old, which means any brown dwarfs there would still be warm, still glowing brightly enough to detect. A team of Spanish astronomers using a telescope in the Canary Islands identified an object that was too faint to be a star, but too bright to be a planet. Its spectrum showed lithium, an element that stars destroy quickly through fusion, but that brown dwarfs preserve. Tidy 1 had lithium. It wasn't fusing, it was a brown dwarf. The announcement sent ripples through the astronomical community. After decades of theory, here was proof. Brown dwarfs were real. The universe did make these in-between objects. And if there was one, there had to be more. Just months later, in October of 1995, another discovery. This one even more dramatic. Astronomers at Palomar Observatory in California, using adaptive optics technology that corrected for atmospheric distortion, captured an image of a faint companion orbiting a small red dwarf star called Gliese 229. The companion, designated Gliese 2029b, was far too dim to be a star. Its spectrum showed methane, a molecule that can only exist in cool atmospheres. Stars are too hot for methane. It burns up. But cool brown dwarfs can have methane in their atmospheres just like gas giant planets do. Gliese 229b was not just a brown dwarf. It was a cool brown dwarf, cooler than anyone had expected to find so soon. Its temperature was estimated at around 900 to 1,000 Kelvin cooler than a candle flame, cool enough that it glowed deep red, almost invisible even in infrared. And there it was, orbiting a star, 49 light-years away, captured in pixels undeniable. The floodgates opened. With better telescopes, better detectors, better techniques, brown dwarfs started appearing everywhere astronomers looked. Surveys like the 2-micron all-sky Survey 2 mass scan the entire sky in infrared, cataloging hundreds of millions of objects. Among them, thousands of brown dwarfs. The Sloan Digital Sky Survey found more. The Wide Field Infrared Survey Explorer, WISE, launched in 2009, found even cooler ones. Brown dwarfs so faint they had been invisible to earlier searches. Each discovery refined our understanding. Scientists developed a classification system for brown dwarfs extending the traditional stellar types. Normal stars are classified as O, B, A, F, G, K, M from hottest to coolest. Our Sun is a G-type star. Red dwarfs are M-type. Brown dwarfs got 3 new categories, L, T, and Y. L dwarfs are the warmest brown dwarfs, still hot enough to glow a dull red. T dwarfs are cooler with methane-dominated atmospheres. And Y dwarfs, discovered more recently, are the coldest known some, with temperatures below the boiling point of water. Think about that for a moment. There are brown dwarfs out there cooler than boiling water, cooler than a hot summer day. Objects the size of Jupiter, dozens of times more massive, but with surface temperatures you could almost tolerate, not that you'd want to visit. The crushing gravity would kill you instantly. But still, the idea is startling. A star or star-like object, cool enough to have weather you might recognize, cool enough for water vapor to condense into clouds. But finding these objects wasn't just about pointing telescopes at random patches of sky and hoping for the best. It required strategy. Astronomers learned to look in places where brown dwarfs were more likely to be found. Young star clusters like the Pleiades, where brown dwarfs were still warm. Nearby regions of space within a few dozen light-years, where even faint objects would be bright enough to detect. Binary systems, where a brown dwarf might orbit a star easier to spot, because you could measure its gravitational influence on its companion. One of the most successful strategies was looking for objects with high proper motion. Proper motion is the apparent movement of an object across the sky over time, caused by its actual motion through space. Stars are so far away that their proper motion is usually tiny, imperceptible, except over decades or centuries. But nearby objects, things within a few light years, can have noticeable proper motion. If you compare images of the same patch of sky taken years apart, a nearby brown dwarf might have shifted position slightly. It's a subtle clue, but a powerful one. Using this technique, astronomers discovered some of the closest brown dwarfs to Earth. In 2013, a pair of brown dwarfs called Lumen 16AB was found just 6.5 light-years away, the third closest known system to our Sun, after Alpha Centauri and Barnard's star. Lumen 16AB is close enough that even amateur astronomers with modest telescopes can spot it if they know where to look and have an infrared filter. These 2 brown dwarfs orbit each other, a binary system, both glowing faintly in the southern sky. And here's what's remarkable. Lumen 16AB was only discovered in 2013, 6.5 light-years away. practically in our cosmic backyard. And we didn't know it was there until recently. It had been there all along, of course, drifting through space, cooling, glowing, but invisible to us, hidden in plain sight. How many more are out there even closer, still waiting to be found? How many brown dwarfs are lurking in the darkness within a few light years of Earth, too faint for our current telescopes to detect? Some estimates suggest there could be brown dwarfs closer than Proxima Centauri, the nearest known star. We just haven't seen them yet. There's something humbling about that. We like to think we know our neighborhood. We've mapped the nearby stars, cataloged the planets, sent probes to the edge of the solar system. But the universe keeps reminding us how much we've missed, how much remains invisible waiting for the right tool, the right moment, the right question. The hunt for brown dwarfs also taught astronomers something important about patience, about persistence. Shiv Kumar proposed the existence of brown dwarfs in 1963. The first one wasn't confirmed until 1995, 32 years. An entire generation of astronomers spent their careers searching for something they might never see. Some of them retired without ever finding one. Some of them doubted late at night whether they were wasting their time. But they kept looking, because the theory was sound, because the math was right, because they believed that nature and its infinite creativity would make these objects even if we couldn't yet see them. And they were right. Brown dwarfs were there all along, billions of them, filling the galaxy, glowing softly in the margins. It makes you wonder what else we're missing. What other populations of objects are out there invisible to current technology waiting for the next breakthrough? What will the astronomers of the future find? Looking back at our catalogs, amazed that we miss something so obvious, so abundant, so close. The universe doesn't reveal itself all at once. It waits. It tests our patience, our ingenuity, our willingness to believe in things we cannot yet see. And when we finally develop the tools, the techniques, the persistence to look in the right way, it rewards us. Not with fanfare, not with explosions, but with quiet revelations. Objects that were always there now visible. Mysteries that become knowable one dim photon at a time. Brown dwarfs were worth the wait. They're strange, beautiful, complex. They challenge our categories, blur our boundaries, remind us that nature is more creative than our imaginations. And now that we can see them, now that we can study them, they're revealing secrets we never expected. Secrets about weather, about chemistry, about the nature of matter under extreme pressure. Secrets that will take us deeper into the in-between, deeper into the margins where the real wonders hide. So, the hunt continues. Not for the first brown dwarf anymore, that question is answered, but for the coolest, the closest, the strangest. For the ones that defy expectations, the ones that teach us something new. And as our telescopes improve, as our techniques sharpen, we'll find more. We'll peer deeper into the darkness and watch as brown dwarfs emerge one by one, glowing softly against the black. Because now we know how to look. Now we know they're there. And the invisible is becoming visible slowly, patiently, in the quiet way that truth always does. There's a question that haunts the study of brown dwarfs, a question without a clean answer. What are they really? Not in the poetic sense, not in the metaphorical sense, but in the practical categorical sense that science demands. Are they stars that failed? Planets that grew too large? Something else entirely? Something that doesn't fit the boxes we've drawn? The universe, it seems, doesn't care much for our boxes. When we look at a brown dwarf, when we measure its mass and temperature and composition, we find something caught between worlds. Too massive to be a planet, not massive enough to be a star. It occupies a liminal space, a threshold, and thresholds are always the hardest places to define. Because a threshold isn't a thing unto itself. It's the moment of transition, the edge, where one category bleeds into another, and brown dwarfs live on that edge, stubbornly refusing to be just one thing. Let's start with mass, because mass is where the boundaries begin. A brown dwarf must have at least 13 times the mass of Jupiter. 13 Jupiter masses written as 13 MJ in scientific notation. Below that, The object is classified as a planet, even if it's enormous, even if it dwarfs anything in our solar system. Above 13 Jupiter masses, deuterium fusion can occur. Deuterium, also called heavy hydrogen, has a neutron, paired with its proton, making it slightly heavier than normal hydrogen. And that extra mass matters. Deuterium fuses at much lower temperatures than hydrogen, around 1,000,000 Kelvin instead of 10 million. So an object with at least 13 Jupiter masses can ignite deuterium in its core, burn it for a few million years, and release energy. That's the lower boundary of a brown dwarf, deuterium burning. But here's where it gets murky. Not all 13 Jupiter mass objects burn deuterium the same way. The exact threshold depends on composition, on how much deuterium is present on the object's age and formation history. Some objects right at the boundary might burn a little deuterium, others might not. The line isn't sharp, it's fuzzy, gradual, a zone rather than a point. And then there's the upper boundary. A brown dwarf can be as massive as about 80 Jupiter masses, or roughly 0.08 solar masses. Above that, the core gets hot enough to fuse hydrogen. Hydrogen fusion is the defining characteristic of a true star. Once that starts, the object stabilizes. It becomes a red dwarf, the smallest type of main sequence star, and it will burn steadily for trillions of years. Below 80 Jupiter masses, hydrogen fusion never begins. The object is a brown dwarf. It will cool, dim, fade. So brown dwarfs exist in this range, 13 to 80 Jupiter masses. That's the mass window. But mass alone doesn't tell the whole story, because how an object forms matters just as much as how massive it is. Planets form in disks. When a star is born, it's surrounded by a swirling disk of gas and dust, the leftover material from the collapsing cloud. Over millions of years, particles in that disk stick together, growing into pebbles, boulders, planetesimals, eventually planets. This process is called accretion. It's bottom-up construction, small things combining into bigger things. Gas giants like Jupiter form this way too. They start as rocky cores that grow massive enough to pull in gas from the surrounding disk. But they form in orbit around a star. They're part of a planetary system. Brown dwarfs, on the other hand, form like stars. They condense directly from a collapsing cloud of gas. There's no disk, no accretion, no gradual buildup. The cloud fragments, and one of those fragments becomes a brown dwarf. It's top-down formation. The object collapses under its own gravity, heats up, and settles into equilibrium. It might form alone, or it might form in a binary system with another brown dwarf, or a star. But it doesn't form in a disk around something else. So here's the distinction scientists have settled on. If it forms from a collapsing cloud and can burn deuterium, it's a brown dwarf. If it forms in a disk around a star and never burns anything, it's a planet. That's the rule. That's how we draw the line. But nature, as always, complicates things. There are objects called planetary mass brown dwarfs, or sometimes rogue planets that formed like brown dwarfs from collapsing clouds, but have masses below 13 Jupiters. They never burned deuterium. They just cooled. Are they planets, or are they brown dwarfs? The formation says brown dwarf. The mass says planet. Scientists are still debating. And then there are super Jupiters, massive planets discovered around other stars, some with masses pushing close to 13 Jupiters. Did they form in a disk, or did they form independently and later get captured by a star? We don't always know. We can't always tell. The universe makes what it makes, and sometimes those creations sit right on the boundary, defying our attempts to label them. It's frustrating in a way. We want clarity. We want to point at an object and say, definitively, this is a planet, or this is a brown dwarf, or this is a star. But the universe doesn't owe us that clarity. It blurs the lines. It challenges our categories. And maybe that's the point. Let's talk about composition. Brown dwarfs are made mostly of hydrogen and helium, just like stars, just like gas giant planets. But as they cool their atmospheres, develop complex chemistry. Scientists studying brown dwarf spectra have found evidence of water, vapor methane ammonia, carbon monoxide. These are molecules you'd expect to find on a planet not a star. Stars are too hot for molecules. Their heat tears everything apart into individual atoms. But brown dwarfs, especially cool ones, can support molecular chemistry. Their atmospheres are more like Jupiter's atmosphere than like the Sun's. Some brown dwarfs even have clouds. Not water clouds, not the kind you see in Earth's sky, but clouds made of silicates, minerals, tiny grains of sand and dust, suspended in the atmosphere. Research shows that these clouds can form layers stratified by temperature and pressure. Higher up, where it's cooler, one type of cloud. Deeper down, where it's warmer, another type. And these clouds affect how the brown dwarf looks, how bright it appears, what wavelengths of light it emits. Temperature is another way to understand the in-between nature of brown dwarfs. The hottest brown dwarfs, young ones still glowing from their formation, can reach temperatures of 2000 Kelvin or more. Hot enough to glow a deep red. Hot enough that you could see them with your eyes, if you were close enough, a dull ember against the black. But as they age, they cool. After 1 billion years, a brown dwarf might be down to 1000 Kelvin. After 10 billion years, maybe 500 Kelvin cooler than the hottest lava on Earth, cooler than a pizza oven. And the coolest brown dwarfs, the Y dwarfs we mentioned earlier, can be as cold as 300 Kelvin or less. That's around 80 degrees Fahrenheit, a warm summer day. Some Y dwarfs might even be cooler than the human body, imagine that. An object the size of Jupiter, dozens of times more massive with surface temperatures, you could theoretically survive, at least in terms of heat. Not that you'd want to be there. The gravity would crush you, the atmosphere would be toxic, but the temperature would almost be comfortable. It raises an interesting question. At what point does a brown dwarf stop being star-like and start being planet-like? Is it when the temperature drops below a certain threshold? When methane appears in the spectrum, when clouds form, there's no consensus. Different scientists draw the line in different places. And maybe there shouldn't be a line at all. Maybe brown dwarfs are their own category, distinct from both stars and planets, occupying their own unique space in the cosmic taxonomy. One way to think about it is in terms of energy. Stars generate energy through fusion. They're active, dynamic, self-sustaining. As long as they have fuel, they shine. Planets, on the other hand, don't generate significant energy. They might have residual heat from a formation like Jupiter or tidal heating, from gravitational interactions like some of Jupiter's moons, but they're not powered by fusion. They're passive reflective, dependent on external sources of energy. Brown dwarfs fall somewhere in between. They generate some energy, yes, from deuterium fusion early on, and from the slow release of gravitational potential energy as they contract and cool. But that energy output is tiny compared to a star. A brown dwarf doesn't sustain itself. It doesn't reach equilibrium the way a star does. It just fades. Slowly, over billions of years, it radiates away the heat of its birth, growing dimmer and dimmer until it's nearly invisible. So, in a sense, brown dwarfs are dying from the moment they're born. They never achieve the stability of a star. They never settle into a long-lived main sequence. They just cool, slowly, inevitably, like embers pulled from a fire, still glowing, but fading, fading, fading. There's a melancholy to that, isn't there? The idea of an object that never quite becomes what it could have been. An object defined by what it lacks rather than what it has. But maybe that's the wrong way to think about it. Maybe brown dwarfs aren't defined by their failures. Maybe they're defined by their existence. They are. They glow. They have structure, complexity, beauty. They don't need to be stars to matter. And in fact, brown dwarfs might teach us more about the universe than stars do. Because they exist on the boundary, they help us understand where that boundary is. They test our models of formation, of fusion, of atmospheric chemistry. They challenge our assumptions. They force us to think more carefully about what we mean when we say star or planet or object. They expand our vocabulary, our conceptual framework, our understanding of what the universe can create. Consider Jupiter for a moment. Jupiter is the largest planet in our solar system, 318 times the mass of Earth. It's massive enough to generate its own heat, radiating about 1.6 times as much energy as it receives from the sun. It has a magnetic field powered by metallic hydrogen in its core. It has storms that have raged for centuries, the Great Red Spot being the most famous. It has moons, dozens of them, some with subsurface oceans, some possibly harboring life. Jupiter is extraordinary, but Jupiter is also firmly a planet. It has only about 0.1% the mass needed to fuse hydrogen. It's not even close to the 13 Jupiter mass threshold for deuterium burning. It formed in a disk around the sun. It's part of a planetary system. There's no ambiguity. Now, imagine an object with 15 times Jupiter's mass. It formed from a collapsing cloud just like a star. It burned deuterium for a few million years. It glows faintly in infrared. Is it more like Jupiter or more like the sun? The answer is neither. It's a brown dwarf. It's its own thing, and that's the beauty of it. The universe doesn't just make stars and planets. It makes a whole spectrum of objects, each with its own properties, its own history, its own place in the cosmic ecosystem. Brown dwarfs are part of that spectrum. They fill a niche. They exist because the laws of physics allow them to exist. And they remind us that nature is more creative, more varied, more surprising than our categories can capture. So, when we ask what is a brown dwarf, the answer is complicated. It's an object between 13 and 80 Jupiter masses. It forms from a collapsing cloud. It might burn deuterium briefly. It cools over time. It has an atmosphere, possibly clouds, possibly weather. It glows in infrared. It's not a star. It's not a planet. It's something else. Something in between. Something that defies easy definition. And maybe that's okay. Maybe the universe is trying to teach us that not everything needs a label. Not everything fits neatly into the boxes we've prepared. Some things exist on thresholds and transitions in the spaces we didn't think to name. And those are often the most interesting things of all, because they challenge us. They make us think harder, look closer, question our assumptions. They remind us that the cosmos is vast, strange, full of surprises. Brown dwarfs are one of those surprises. A whole population of objects we didn't know existed living in the margins, glowing softly, waiting to be understood. And now that we've found them, now that we're studying them, they're revealing themselves slowly, one spectrum at a time, one temperature measurement at a time, one cloud layer at a time. And with each revelation, the boundary between star and planet becomes a little less clear, and the universe becomes a little more beautiful. A little more complex, a little more worthy of wonder. And that wonder will carry us forward into the next chapter of their story, where the cooling begins in earnest and time itself becomes the main character. Time moves differently for a brown dwarf, not in the relativistic sense, not in the warping of space-time that happens near black holes or at speeds close to light, but in the quiet, patient sense of an existence stretched across eons. If you could watch a brown dwarf from birth to its final dimmest state, you would need to wait billions of years, tens of billions, perhaps hundreds of billions. Time scales so vast that the human mind struggles to hold them. But that's the life of a brown dwarf, a long, slow fade, a cooling that never quite ends. Imagine being born warm, glowing with the heat of your own compression, bright enough to be seen across light years. Then imagine that warmth seeping away degree by degree, century by century, until you're barely warmer than the space around you. That's what happens to every brown dwarf ever formed. They're born hot, and they spend the rest of eternity cooling down. Let's trace that journey slowly the way a brown dwarf would want us to. When a brown dwarf first condenses from a collapsing cloud of gas, it's hot. The gravitational energy released during the collapse converts into thermal energy. The core temperature can reach a few million Kelvin hot, enough to glow hot enough to radiate light. For a young brown dwarf, most of that light is in the near-infrared, invisible to human eyes, but detectable with the right instruments. If you could see infrared, a newborn brown dwarf would look like a deep red coal, bright and fierce. And for a brief moment, cosmically speaking, something extraordinary happens. If the brown dwarf has enough mass, at least 13 times Jupiter's mass, the core gets hot enough to fuse deuterium. Deuterium is rare only about 20 parts per million in the universe's hydrogen supply, but it's there. And when deuterium nuclei collide with enough energy, they fuse. They combine into helium-3, releasing energy in the process. Not as much energy as hydrogen fusion, not enough to stabilize the brown dwarf the way a star stabilizes, but enough to slow the cooling to add a little extra glow. This deuterium burning phase lasts a few million years, maybe 10 million at most. Scientists suggest that for the most massive brown dwarfs, those near the 80 Jupiter mass boundary deuterium, burning can extend the warm phase significantly. But eventually, the deuterium runs out. There's just not enough of it. The fusion stops. And from that moment on, the brown dwarf relies entirely on its residual heat, the warmth left over from its formation. And that warmth slowly, inevitably radiates away into the coldness of space. This is where the long cooling begins. This is where time becomes the story. A brown dwarf doesn't have an internal furnace to maintain its temperature. It's not like a star where fusion in the core generates energy that balances the gravitational collapse, creating a stable equilibrium that lasts for billions or even trillions of years. A brown dwarf is more like a hot stone pulled from a fire. It starts out warm, but with no source of heat to sustain it, it cools. The only question is, how fast? The answer is slowly, very slowly. Because brown dwarfs are large, and large objects cool more slowly than small ones. The surface area to volume ratio matters. A brown dwarf might be the size of Jupiter, but it's dozens of times more massive, packed with more matter, more energy. That energy takes time to dissipate. The surface radiates heat into space, yes, but the interior stays warm for a long time, conducting heat outward at a gradual pace. Research shows that a typical brown dwarf cools at a rate of about 1 Kelvin every million years. 1 degree per million years. Think about that. If you watched a brown dwarf for your entire life for 100 years, its temperature would drop by about 1/10,000th of a degree. Imperceptible, unmeasurable in human timescales. But over 1 billion years, it would cool by 1,000 degrees. Over 10 billion years, 10,000 degrees. Slowly the ember dims, and as it cools, it changes. The spectrum shifts. The color, if we could see it, would darken. A young hot brown dwarf glows red. An older, cooler one glows deep crimson, then infrared, then nearly invisible. The atmospheric chemistry changes too. At high temperatures, certain molecules can't exist. They're torn apart by the heat. But as the brown dwarf cools, molecules begin to form. Water vapor appears. Methane condenses. Ammonia crystals might form in the upper atmosphere. The brown dwarf transforms chemically as it ages. Scientists have observed brown dwarfs at different stages of this cooling process. By studying their spectra, their brightness, their temperatures, we can piece together the timeline. We can see what a brown dwarf looks like at 10 million years old, at 100 million years, at 1 billion years. Each snapshot is a different object, of course, but together they tell the story of one life, one long cooling. At 10 million years, a brown dwarf might still be at 1500, Kelvin glowing a dull red. Its spectrum shows lithium still intact, not yet destroyed. Clouds of dust and silicates might form in its atmosphere, swirling, thickening, creating bands and zones like we see on Jupiter. At 100 million years, the temperature has dropped to around 1,000 Kelvin. Methane begins to appear in the spectrum. The glow shifts deeper into the infrared. The brown dwarf is dimmer now, harder to see, but still warm. At 1 billion years, it's down to 600 or 700 Kelvin. The surface is cooler than molten lava, cooler than the hottest ovens on Earth. The light is almost entirely infrared. To see it, you'd need specialized detectors. It's no longer red, not even to infrared eyes. It's a deep, dark glow barely distinguishable from the background. At 10 billion years, the temperature might be 3 or 400 Kelvin, cool enough that the brown dwarf could, in theory, have water ice clouds in its upper atmosphere, cool enough that the physics starts to resemble a planet more than a star. And yet, it's still glowing, still radiating the last remnants of its birth heat into space. And it keeps going. 50 billion years. 100 billion years. The universe itself is only about 14 billion years old, so we're speculating now, extrapolating from models and mathematics. But the models suggest that brown dwarfs will continue cooling for unimaginable spans of time. Eventually, they'll reach the temperature of the cosmic microwave background radiation, the faint glow left over from the Big Bang, which currently sits at about 3 Kelvin. At that point, billions upon billions of years in the future, the brown dwarf will be in thermal equilibrium with the universe. It will stop cooling not because it's run out of heat, but because there's nowhere cooler for the heat to go. But even then it won't die. It will just exist cold and dark, a frozen sphere of hydrogen and helium drifting through the void. A relic, a memory of a star that never was. There's something profoundly patient about that existence. No drama, no supernova, no collapse into a black hole. Just a slow, steady release of energy across time scales that dwarf civilizations, species, perhaps even galaxies. A brown dwarf outlasts almost everything. Stars burn out. Planets lose their atmospheres, get swallowed by their suns, collide and shatter. But brown dwarfs just cool, quietly, persistently, forever. It makes you think about legacy, doesn't it? About what it means to last. We often associate longevity with brightness, with burning hot and fierce. But brown dwarfs teach a different lesson. They last not by burning, but by refusing to burn. By holding on to their warmth as long as they can, releasing it slowly, reluctantly into the cold. There's a kind of quiet dignity in that. And here's something remarkable. Because brown dwarfs cool so slowly, we can use them as clocks. We can measure their temperature, compare it to models of cooling, and estimate their age. The cooler a brown dwarf, the older it is. This technique has been used to age-date star clusters, regions of space, where many stars and brown dwarfs formed at roughly the same time. By finding the coolest brown dwarfs in a cluster, astronomers can say this cluster must be at least this old, because it takes this long for a brown dwarf to cool to this temperature. It's a subtle method requiring careful observations and detailed models, but it works. Brown dwarfs and their slow cooling have become tools for understanding the history of the galaxy. They're not just objects to study, they're witnesses. They've been around for a long time, some of them nearly as old as the galaxy itself, and they carry that history in their temperature, in their glow. But the cooling process isn't perfectly smooth. Brown dwarfs don't just sit still and radiate heat evenly. They're dynamic objects. They rotate sometimes very quickly. Some brown dwarfs spin once every few hours faster than Earth. That rotation affects how heat is distributed across the surface. The equator might be warmer than the poles. Hotspots might develop regions where upwelling brings warmer material to the surface, creating bright patches that rotate in and out of view. Scientists have observed this. By watching a brown dwarf over several hours or days, they can see its brightness change, flickering slightly as hotspots rotate in and out of view. It's similar to how we can tell a planet is rotating by watching its brightness vary, or how we can map the surface of a distant star by measuring tiny changes in its light. Brown dwarfs, despite being dim, are not featureless. They have structure. They have weather in a sense. And that weather affects the cooling. Convection plays a role too. Inside a brown dwarf, heat moves from the core to the surface through convection, the same process that makes water boil, the same process that drives Earth's weather. Hot material rises, cools at the surface, and sinks back down. This creates currents, flows, patterns of motion that distribute heat. The more efficient the convection, the faster the cooling, at least in the short term. But these are slow processes operating over millions of years, not days, or weeks. And then there's the question of what happens to the interior. As a brown dwarf cools, the pressure at the center remains enormous, crushing. Matter there exists in exotic states. At the core, hydrogen might be in a metallic form, electrons stripped away, allowing the hydrogen to conduct electricity. This metallic hydrogen is thought to exist in Jupiter's interior as well, and it's responsible for Jupiter's powerful magnetic field. Brown dwarfs likely have magnetic fields too, generated by the motion of metallic hydrogen in their cores. These fields can be stronger than Earth's, strong enough to trap charged particles, create aurorae, influence the atmosphere. But we're still learning. Magnetic fields on brown dwarfs are difficult to measure. We infer them from radio emissions, from patterns in the light from theoretical models. But direct observations are rare. Brown dwarfs are teaching us slowly how matter behaves under these extreme conditions. How it cools, how it flows, how it generates magnetism. And with each discovery, we refine our models not just of brown dwarfs, but of planets of stars of matter itself. It's worth asking, what does it feel like to cool for billions of years? Obviously, brown dwarfs don't feel anything in the way we do. They're not conscious. They're clouds of gas held together by gravity. But if we think metaphorically, poetically, what is that experience, to be born in a blaze of compression, to glow brightly for a moment, and then to spend the rest of eternity fading slowly into darkness? Is it peaceful? Is it lonely? Is it simply inevitable, the way all things in the universe move toward equilibrium, toward coldness, toward stillness? The second law of thermodynamics tells us that entropy always increases. That order tends toward disorder, that heat flows from hot to cold, that everything eventually cools down. Stars fight this for a while by fusing elements, generating energy, maintaining their heat. But even stars eventually run out of fuel. They cool too in the end, becoming white dwarfs, neutron stars, black holes. Everything cools. Brown dwarfs just do it more honestly. They never pretended to be anything other than what they are. They started cooling from day one. They never fought it. They just let it happen gracefully across the eons. And maybe there's wisdom in that. Not fighting the inevitable, not clinging to warmth that's destined to fade, just existing fully at every temperature, at every stage, accepting the slow transformation without resistance. From a glowing ember to a cold, dark sphere, each moment is what it is. No more, no less. The universe is cooling too, in a sense. The cosmic microwave background radiation, that faint afterglow of the Big Bang, gets cooler as the universe expands. Right now, it's at about 2.7 Kelvin. In 1 trillion years, it will be cooler still. Eventually, if current models are correct, the universe will reach a state called heat death, where all energy is evenly distributed, all stars have burned out, all black holes have evaporated, and nothing can happen anymore because there's no temperature difference to drive processes. Everything will be the same temperature, cold, still, silent. Brown dwarfs will still be there though, floating in the dark, indistinguishable from the background, no longer glowing, no longer changing, just existing. Witnesses to the universe's long, slow cooling, companions to the end. But that's trillions of years away. For now, brown dwarfs are still glowing. Still cooling, yes, but still warm enough to see if we look carefully. Still teaching us about the nature of matter, of time, of existence. And in their patient fading, they remind us that endings can be gentle, that not everything needs to explode to be significant, that sometimes the most profound stories are the ones told quietly over unimaginable lengths of time in the margins of the universe where no one is watching. Except, of course, we are watching now. We're listening. And the brown dwarfs cooling patiently have so much more to show us as we drift deeper into their strange and beautiful atmospheres. What does the sky look like on a brown dwarf? It's a strange question, one that requires us to imagine standing on the surface of an object that doesn't really have a surface, not in the way Earth does. Brown dwarfs are gas through and through layers of hydrogen and helium, compressed by gravity growing denser toward the core. There's no ground to stand on, no solid boundary between atmosphere and interior. Just pressure increasing gradually as you descend until the gas becomes liquid, then something stranger still. But if you could somehow float at a particular pressure level suspended in the upper atmosphere of a brown dwarf, what would you see? What would the weather be like? The clouds, the winds, the storms that rage across these failed stars. The answer is violent, beautiful, utterly alien. Brown dwarf atmospheres are not calm. They're churning dynamic systems where physics plays out in extreme ways. Winds scream across the surface at speeds that make Earth's hurricanes look gentle. Clouds form from materials that would be solid or liquid on Earth, minerals and metals vaporized by heat, then condensing into droplets and crystals as they rise and cool. And storms that dwarf anything we've ever witnessed, can persist for decades, centuries, maybe longer, driven by the convection of heat from deep within. Let's start with the clouds, because clouds are one of the most surprising features of brown dwarfs. When astronomers first started studying brown dwarf spectra in detail, they noticed something odd. The brightness would vary over time, not randomly, but in patterns. A brown dwarf would brighten, then dim, then brighten again, with a regular period. The period matched the rotation rate of the brown dwarf, a few hours typically. This suggested that the surface wasn't uniform. There were regions that were brighter, hotter, and regions that were dimmer, cooler. And as the brown dwarf rotated, these regions came into view and then disappeared again, causing the brightness to change. But what could create these variations? Stars don't have this problem. Their surfaces are relatively uniform, heated from within by fusion smoothed out by convection and radiation. Planets can have atmospheric variations, bands of clouds like Jupiter's storms, like Neptune's great dark spot. But brown dwarfs are somewhere in between. They're not heated by fusion, so their energy comes from cooling and contraction. And that creates instabilities regions where hot material rises and cool material sinks, forming patterned structures, clouds. Research shows that brown dwarf clouds are made of exotic materials. At the temperatures of L-type brown dwarfs, around 1200 to 2000, Kelvin silicate clouds can form. Silicates are minerals, the stuff of sand and rock on Earth. But in a brown dwarf's atmosphere, silicates vaporize, mix with the gas, and then condense into tiny grains at higher altitudes where it's cooler. These grains form clouds, layers of suspended particles that scatter light, that absorb and re-emit infrared radiation that affect how bright the brown dwarf appears. Imagine clouds made of sand, not water vapor, not ice crystals, but molten droplets of rock and metal floating in an atmosphere of hydrogen and helium. That's what scientists believe exists on hot brown dwarfs. And these clouds don't just sit there. They're carried by winds blown into bands and zones stretched and twisted by the brown dwarf's rapid rotation. As brown dwarfs cool, the cloud composition changes. T-type brown dwarfs, cooler than L-types, have temperatures between 700 and 1200 Kelvin. At these temperatures, silicate clouds sink deeper into the atmosphere below the visible layers, but new clouds form made of different materials. Water clouds, ammonia, clouds, even clouds of salts like sodium chloride and potassium chloride, table salt floating in the sky. It sounds impossible, but the physics allows it. At certain pressures and temperatures, these compounds can condense out of the gas and form clouds just like water vapor condenses into clouds on Earth. And the coolest brown dwarfs, the Y-types, might have water ice clouds. Actual ice, the same kind that forms on Earth, suspended in an atmosphere that's only a few hundred Kelvin. It's a strange inversion. An object the size of Jupiter, dozens of times more massive with clouds you could almost recognize. Clouds made of frozen water drifting through skies lit only by the faint infrared glow of residual heat. But clouds are just one part of the story. The winds are another. Brown dwarfs rotate quickly, and that rotation drives powerful atmospheric currents. The Coriolis affect the same force that curves hurricanes on Earth, acts on brown dwarf atmospheres too, creating jet streams eastward and westward flows that encircle the object. These jets can reach speeds of hundreds, even thousands of miles per hour. Some brown dwarfs have equatorial jets moving faster than the speed of sound in their atmospheres. Think about that. Winds faster than sound. On Earth, the fastest winds we see are in tornadoes and jet streams, maybe 200 miles per hour at most. On Jupiter, winds can reach 400 miles per hour. But on brown dwarfs, the winds can exceed 1,000 miles per hour, driven by the temperature differences between the hot interior and the cooler upper atmosphere, accelerated by the rapid rotation. And these winds don't just move in straight lines. They create vortices, eddies, storms. Scientists studying brown dwarfs have found evidence of storm systems that resemble Jupiter's Great Red Spot, massive anticyclonic storms that persist for long periods. These storms are regions of high pressure where gas rotates trapped in a stable pattern, resistant to disruption. On Jupiter, the Great Red Spot has lasted for at least 300 years, possibly longer. On a brown dwarf, a similar storm might last even longer, centuries or millennia, a permanent feature of the atmosphere. One of the most studied brown dwarfs in terms of atmospheric dynamics is Lumen 16AB, the binary system we mentioned earlier. Lumen 16A and B orbit each other at a distance of only about 3 astronomical units, roughly the distance from the Sun to the asteroid belt. They're both brown dwarfs, both relatively cool around 1300 Kelvin for Lumen 16A and 1100 Kelvin for Lumen 16B, and both show brightness variations consistent with patchy cloud cover. In 2014, astronomers used the Hubble Space Telescope to create a crude map of Lumen 16B's surface. They couldn't resolve the brown dwarf directly. It's too small and too far away for that. But by watching how the brightness changed as it rotated, they could infer where the bright and dark regions were. They created a map, the first of its kind, showing bands and spots, regions of thick clouds and regions of thinner clouds. It was rough, low resolution, but it was a start. It proved that we can map brown dwarf atmospheres, that we can study their weather patterns, that these objects are not featureless blobs, but complex, dynamic worlds. And here's something fascinating. The atmosphere of a brown dwarf is stratified, layered by temperature and pressure. Near the visible surface, the photosphere conditions are relatively cool, but deeper down, the temperature and pressure increase. And as you go deeper, different materials condense at different levels, creating layers of clouds stacked on top of each other. A brown dwarf might have a layer of silicate clouds below a layer of water, clouds above, and a clear region in between. Or the clouds might mix, creating a hazy complex structure. This layering affects how light escapes. Infrared radiation from the hot interior tries to rise to the surface and radiate into space, but clouds absorb and scatter that radiation. Thick clouds can trap heat, acting like a blanket, keeping the deeper layers warmer. Thin clouds let more heat escape. So, the distribution of clouds affects the cooling rate, affects the temperature structure, affects everything. It's a feedback loop. Heat rises, creating convection, which forms clouds, which trap heat, which affects convection, which changes the clouds. The atmosphere is constantly adjusting, seeking equilibrium, but never quite finding it, because the heat source, the cooling interior, is always changing. It's a dynamic system, chaotic in the technical sense, sensitive to small changes, unpredictable in detail, but governed by the same fundamental physics. And then there's the question of precipitation. On Earth, clouds produce rain, snow, hail. Water condenses, grows heavy, and falls. On brown dwarfs, the same process might occur, but with different materials. Silicate clouds might produce rain made of molten sand droplets falling through the atmosphere until they evaporate in the hotter layers below. Salt clouds might produce snow made of sodium chloride crystals. Water ice clouds might produce actual snow-frozen water, falling through a hydrogen-helium atmosphere, a surreal inversion of earthly weather. Scientists call this exotic precipitation. It's never been observed directly, but the physics suggests it should happen. And if it does, it would be part of the convection cycle. Droplets form, fall, evaporate, and the vapor rises again, condenses, falls, over and over. A vertical circulation driven by gravity and heat, redistributing material, mixing the atmosphere. There's also the possibility of lightning. On Earth, lightning forms in thunderstorms when ice particles collide, building up electrical charge that eventually discharges in a flash. On Jupiter and Saturn, spacecraft have detected lightning-powerful bolts that dwarf anything on Earth. On brown dwarfs, the conditions might be right for lightning too. Clouds of particles, rapid convection charge separation. Some astronomers have speculated that brown dwarfs could have lightning storms far more intense than anything in our solar system, bolts arcing across hundreds of miles, illuminating the clouds briefly before fading. But detecting lightning on a brown dwarf would be incredibly difficult. We'd need to catch the brief flash, a spike in brightness at visible or radio wavelengths, and distinguish it from other sources of variability. So far, no one has confirmed lightning on a brown dwarf, but the search continues. And what about aurorae? On Earth, aurorae occur when charged particles from the sun, carried by the solar wind, interact with our magnetic field and atmosphere, creating glowing curtains of light near the poles. Jupiter and Saturn have aurorae too, some of the most spectacular in the solar system, powered by their strong magnetic fields and rapid rotation. Brown dwarfs likely have magnetic fields generated by the motion of conductive material in their interiors. And if they do, they might have aurorae. In fact, astronomers have detected radio emissions from some brown dwarfs that could be caused by auroral processes. These emissions vary with the rotation of the brown dwarf, suggesting they're tied to magnetic activity near the poles. If brown dwarfs have aurorae, they would be invisible in optical light. The atmosphere is too dim for that, but they might glow in radio wavelengths, creating bursts of radiation that we can detect from Earth. Imagine that. A brown dwarf alone in space with shimmering aurorae at its poles, flickering in radio waves invisible to the eye, but dancing nonetheless in the magnetic storms of a failed star. It's easy to think of brown dwarfs as static, boring objects. They don't fuse, they don't shine, they just cool. But the more we study them, the more we realize how dynamic they are. Their atmospheres are alive, in a sense constantly moving, changing, reacting to internal heat and external forces. They're weather systems on a cosmic scale laboratories where we can study atmospheric physics under conditions that don't exist anywhere else. And they challenge our assumptions. We think of weather as something that happens on planets. We think of atmospheres as thin layers surrounding solid bodies. But brown dwarfs remind us that atmospheres can be thick, that they can be the entire object that weather can happen, in places with no ground, no ocean, no familiar reference point. Just layers of gas churning, flowing, forming clouds and storms and winds that would tear apart anything we could send there. There's a lesson in that complexity. The universe doesn't simplify itself for our convenience. It creates systems that are messy, chaotic, beautiful in their intricacy. Brown dwarf atmospheres are one example. They're not easy to understand. They require sophisticated models, careful observations, years of study. But they're worth it. Because in understanding them, we understand something fundamental about how matter behaves, how heat moves, how complexity emerges from simple rules. And maybe that's the real beauty of brown dwarfs. Not just that they exist, but that they're so much more interesting than we expected. They're not failed stars in the sense of being incomplete or broken. They're complete unto themselves. They have structure dynamics history. They have clouds made of sand and salt and ice. They have winds that scream across hemispheres. They have storms that last for centuries. They have weather. And that weather, strange as it is, connects them to us. Because weather is something we understand, something we experience. We know what it's like to watch clouds drift across the sky, to feel the wind on our faces, to hear thunder rumble in the distance. Brown dwarf weather is alien, yes, but it's still weather. It's still the movement of gas and energy governed by the same laws of thermodynamics and fluid dynamics that govern Earth's atmosphere. The materials are different, the scales are different, but the principles are the same. So, when we look at a brown dwarf and see brightness variations caused by patchy clouds, we're not just seeing data, we're seeing weather. We're seeing a sky strange and distant, but a sky nonetheless. And in that sky, storms are raging, winds are howling, clouds are forming and dissolving, all driven by the slow cooling of an object that almost became a star. It's a reminder that the universe is full of skies, full of weather, full of atmospheres swirling and churning in the dark. And now, having glimpsed these strange skies, we can turn our gaze to the coldest brown dwarfs of all, where even stranger phenomena await. There are brown dwarfs out there so cold, so dim, that they barely deserve to be called dwarfs at all. They don't glow red. They don't shine in near infrared. They're so faint that most telescopes would look right past them, seeing only empty space where in fact, there's an object, massive ancient cooling, quietly in the dark. These are the wide dwarfs, the coldest class of brown dwarfs known, and they represent the final stage of brown dwarf evolution, the end point of that long cooling we've been tracing. If brown dwarfs are the embers of the cosmos, wide dwarfs are the coals that have almost gone out. Almost, but not quite. They're still there, still real, still glowing if you know how to look. And they're teaching us things we never expected to learn. The classification of brown dwarfs into LT and Y types is based on temperature and spectral characteristics. L dwarfs are the hottest glowing, between about 1200 and 2000 Kelvin. T dwarfs are cooler, 700 to 1200 Kelvin, with strong methane absorption in their spectra. And Y dwarfs, the coldest fall below 500 Kelvin. Some are even cooler than that. Some approach the temperature of a freezing winter day on Earth. 500 Kelvin is roughly 440 degrees Fahrenheit, or 227 degrees Celsius. That's hot compared to Earth's average, yes, but cold for an astronomical object. Cold enough that the chemistry changes entirely. Cold enough that ammonia, which boils at a much lower temperature than water, can condense into clouds. Cold enough that water itself might exist as vapor liquid droplets or ice, depending on the altitude and pressure. The first Y dwarf was discovered in 2011 by NASA's Wide Field Infrared Survey Explorer, or WISE. WISE was a space telescope designed to scan the entire sky in infrared wavelengths, cataloging everything that glowed in the mid-infrared. It was perfect for finding cool brown dwarfs objects that had long since faded from visible and near-infrared light, but still emitted faintly at longer wavelengths. And WISE found hundreds of them, brown dwarfs cooler than anything previously known. Among those discoveries was WISE 0855-0714, often shortened to WISE 0855. This object, located about 7.2 light-years from Earth, is one of the coldest brown dwarfs ever found. Its estimated temperature is around 250 Kelvin, roughly minus 23 degrees Celsius, or minus 9 degrees Fahrenheit, colder than the coldest place on Earth, cold enough to freeze water solid. And yet, it's not a planet. It's a brown dwarf, dozens of times more massive than Jupiter, with an atmosphere, possibly clouds, possibly weather, all happening at temperatures we associate with ice and snow. Think about that. An object the size of Jupiter drifting through space just 7 light-years away, cooler than an Arctic winter. It's been there all along, invisible, glowing so faintly that we needed a space telescope to spot it. And it raises a question. How many more Y dwarfs are out there even closer still waiting to be found? Scientists suggest there could be Y dwarfs closer to Earth than any known star. The nearest star system, Alpha Centauri, is about 4.3 light-years away. But a wide dwarf, dark and cold, could be drifting through space at 2 or 3 light years, maybe even closer, and we wouldn't know. It would be invisible to most surveys, too faint to detect, unless we were specifically looking for it with the right instruments. The possibility is tantalizing. Our nearest cosmic neighbor might not be a star at all, but a cold, dark brown dwarf lurking in the void. Finding wide dwarfs is a technical challenge. They emit almost no light at visible wavelengths. Even in near-infrared, they're extremely dim. The bulk of their radiation comes out in the mid-infrared wavelengths between 3 and 30 microns. To detect them, you need a telescope that's sensitive to those wavelengths. And ideally, you need to observe from space where Earth's atmosphere doesn't absorb the signal. WISE was perfect for this. It operated at wavelengths where wide dwarfs shine brightest, relatively speaking. But even with WISE, detecting wide dwarfs required patience. The telescope scanned the same patches of sky multiple times looking for objects that moved. Stars are so far away that they appear stationary even over months or years. But nearby objects, things within a few light years, have noticeable proper motion. They shift position against the background of distant stars. By comparing images taken at different times, astronomers could identify moving objects, potential brown dwarfs. Then they followed up with spectroscopy measuring the object's spectrum to determine its temperature and composition. And if the spectrum showed the right features, low temperature, strong ammonia, absorption, weak or absent methane, it was classified as a wide dwarf. The discovery of wide dwarfs forced scientists to extend the classification system. For decades, the coolest known objects were T-dwarfs, but wide dwarfs are cooler, still requiring a new category. And with each new wide dwarf discovered, the temperature floor dropped. First 500 Kelvin, then 400, then 300, then even lower. WISE 0855 at 250. Kelvin might not be the coldest. There could be brown dwarfs out there at 200 Kelvin or 100 cooling slowly toward the temperature of the cosmic microwave background. And here's where it gets fascinating. At these low temperatures, the atmosphere of a wide dwarf starts to resemble a gas giant planet more than a star. Water vapor can condense into clouds. Actual water clouds, the same kind that exist on Earth. Ammonia clouds form at higher altitudes. The atmospheric pressure and temperature profile might allow for multiple cloud decks, stacked layers of different condensates. It's more like Jupiter or Saturn than like the Sun. But there's a crucial difference. Jupiter is heated by the Sun. It receives energy from an external source, and that energy drives atmospheric dynamics, creates temperature gradients, powers the weather. A wide dwarf has no such external source. It's alone in interstellar space, or, if it orbits a star, it's so far away that stellar heating is negligible. The only energy comes from within, from the residual heat of formation. And that energy is fading. The wide dwarf is cooling slowly but inexorably, and its atmosphere is cooling with it. So, the weather on a wide dwarf, if it has weather, is driven entirely by internal heat. Convection still occurs. Hot material from the interior rises to the surface, cools, and sinks back down. But the convection is weaker than on a hotter brown dwarf. The temperature gradients are smaller. The winds might be slower. The storms might be less intense. It's a quieter atmosphere, more subdued, closer to equilibrium. And yet, research shows that even wide dwarfs can have variability. Astronomers have observed some wide dwarfs with brightness changes over time, suggesting that their atmospheres are not uniform. There are still hot spots and cool spots, regions of thicker and thinner clouds, patterns that rotate in and out of view. The atmosphere is still dynamic even at these frigid temperatures. It's just operating at a lower energy level, like a candle flame compared to a bonfire. One of the most intriguing aspects of wide dwarfs is their potential to host water ice clouds. Water is abundant in the universe, and at temperatures below 273 Kelvin 0 degrees Celsius, water freezes. In the upper atmosphere of a cold wide dwarf, where the pressure is low and the temperature is below freezing water, vapor could condense directly into ice crystals. These crystals would form clouds layers of frozen water, suspended in a hydrogen-helium atmosphere, glittering faintly in infrared light. No one has directly observed water ice clouds on a white dwarf yet. The evidence is indirect, inferred from spectra, from models from the properties of light passing through the atmosphere. But the physics allows it. The conditions are right. And if water ice clouds exist on white dwarfs, they would make these objects even more planet-like, even more familiar, despite their alien nature. Imagine that. A sky filled with ice crystals, not snowflakes drifting down like on Earth, but crystals suspended in a thick atmosphere, held aloft by gentle convection currents, reflecting the faint glow of the brown dwarf's residual heat. It's a surreal image, a failed star with a winter sky. And then there's the question of age. Why dwarfs are old? They have to be. It takes billions of years for a brown dwarf to cool from its formation temperature down to a few hundred Kelvin. A Y dwarf at 250. Kelvin might be 10 billion years old, maybe older. It formed when the galaxy was young, before the sun existed before Earth. And it's been cooling ever since, drifting through space, slowly fading, witnessing the birth and death of stars, the formation of planets, the rise and fall of civilizations on worlds it will never see. There's a kind of loneliness to that existence. White dwarfs are the universe's forgotten objects, too faint to attract attention, too cold to matter in the grand scheme of stellar evolution. They don't explode, they don't collapse, they don't do anything dramatic. They just exist, cooling, fading alone. But they matter to us, because in studying white dwarfs, we're studying the limits of what's possible. We're probing the coldest, dimmest objects that can still be called brown dwarfs. We're testing our models of atmospheric physics, of a cooling of chemistry under extreme conditions. We're learning what happens when matter cools for tens of billions of years, when temperatures drop so low that familiar molecules like water and ammonia dominate the spectrum. And why dwarfs might not be alone. Some scientists speculate that there could be an even colder class of objects, provisionally called ice dwarfs, or frozen dwarfs, brown dwarfs, that have cooled below 100 Kelvin, below the boiling point of nitrogen. At those temperatures, nitrogen itself could condense into clouds. The atmosphere would be dominated by ice is ammonia, ice methane, ice nitrogen ice. The object would be a frozen sphere, barely glowing, nearly indistinguishable from the background radiation of space. No ice dwarf has been confirmed yet. They would be incredibly difficult to detect, too cold, too faint beyond the reach of current telescopes. But they might exist. And if they do, they're out there drifting in the dark, the final stage of brown dwarf evolution, the end of the cooling process that began billions of years ago when a cloud of gas collapsed but didn't gather quite enough mass to become a star. What happens to a brown dwarf after it becomes an ice dwarf? Does it keep cooling forever, approaching absolute zero over trillions of years? Or does it reach some kind of equilibrium, a minimum temperature determined by the faint glow of the cosmic microwave background? Currently about 3 Kelvin. Scientists aren't sure. The timescales involved are so longer than the current age of the universe that we're extrapolating far beyond anything we can observe. But the math suggests that brown dwarfs will keep cooling slowly, asymptotically approaching the temperature of the universe around them, but never quite reaching it. And in that slow approach, they'll persist, long after the sun has died, long after Earth is gone, long after most stars in the galaxy have burned out. Brown dwarfs will still be there, cold, dark, but still massive, still held together by gravity, still real. Witnesses to the universe's long, slow heat death. It's a sobering thought, but also a comforting one in a strange way, because it means that something endures, not the bright things, not the dramatic things, but the quiet things. The things that never burned bright, that never tried to be more than they were. They last, they persist, they outlive the stars. Why dwarfs are a reminder that endings can be gentle, that not everything fades into nothingness. Some things just get quieter, colder, dimmer, but they stay. They remain. And maybe that's a kind of victory. Not against entropy. Entropy always wins, but a victory of persistence, of being, of existing for as long as the laws of physics allow. So, when we look for dwarfs, when we scan the sky with infrared telescopes, hoping to catch the faint glow of an object cooler than winter, we're not just doing science. We're bearing witness. We're acknowledging the existence of these ancient, cold, forgotten things. We're saying, we see you. You matter. Your story is part of the universe's story. And that story is far from over. Because dwarfs, cold as they are, might have surprises left. They might have planets. They might have moons. They might just possibly harbor conditions where something unexpected could happen. And that's where we turn next to the question of worlds of companions, of whether these failed stars and their quiet cooling might be home to something other than themselves. Can a failed star have children? Can something that never quite became what it was meant to be still create something else, something new, orbiting quietly in the faint warmth it provides? The question sounds almost metaphorical, but it's entirely literal. Can brown dwarfs have planets? And if they can, what would those worlds be like circling an object that glows only in infrared, that cools over billions of years, that exists in the margins between star and planet? The answer, it turns out, is yes. Brown dwarfs can have planets. We found them. And they're stranger than anyone expected. When we think of planets, we usually think of them orbiting stars. Earth orbits the sun. Jupiter orbits the sun. Every planet we knew about for most of human history was part of our solar system, bound to a star that provided light and heat. But in recent decades, as our telescopes improved, and our detection methods became more sophisticated, we started finding planets around other stars. Exoplanets, thousands of them, in a dazzling variety of configurations. Hot Jupiters orbiting closer to their stars than Mercury orbits the sun. Super-Earths, rocky worlds larger than our own. Ice giants, gas giants, planets in binary star systems, planets orbiting dead stars. And then, in 2004, astronomers discovered something new, a planet orbiting a brown dwarf. The brown dwarf is called 2M1207, located about 170 light-years away in the constellation Centaurus. It's a young brown dwarf, only about 8 million years old, still warm from its formation, glowing at around 2500 Kelvin, and orbiting it at a distance of about 40 astronomical units, roughly the distance from the Sun to Pluto, is an object about 5 times the mass of Jupiter. This object, designated 2M1207b, was the first planet ever directly imaged around a brown dwarf. Direct imaging is difficult. Most exoplanets are found indirectly by measuring the wobble they cause in their host star's motion, or by detecting the dip in brightness when they pass in front of the star. But 2M1207b was bright enough and far enough from its brown dwarf host that it could be seen directly in infrared images. It appeared as a faint point of light next to the brighter brown dwarf, separated by just enough distance to be resolved as a distinct object. The discovery raised immediate questions. How did this planet form? Did it form in a disk around the brown dwarf, the same way planets form around stars? Or did it form independently and later get captured by the brown dwarf's gravity? Scientists aren't entirely sure. The mass ratio is unusual. 2M207b is about 5 Jupiter masses, and 2M207 is about 25 Jupiter masses. That's a ratio of 1 to 5, much closer than the typical planet-to-star ratio. In our solar system, Jupiter is about 1,000th the mass of the Sun, so is 2M1207b. More like a planet, or more like a binary companion, a smaller brown dwarf orbiting a larger one. The terminology gets fuzzy here, just like it does with brown dwarfs themselves. Some scientists call 2M1207b a planet. Others call it a planetary mass companion, or even a sub-brown dwarf. The formation mechanism matters. If it formed in a disk, it's a planet. If it formed from the same collapsing cloud as 2M.207, just in a separate fragment, it's more like a binary brown dwarf system. But we don't always know how these objects formed. We can only observe them as they are now measure their properties and make educated guesses. Regardless of the semantics, the existence of 2M.127b proved something important. Brown dwarfs can have companions. They can exist in systems with other objects orbiting them. And if one brown dwarf can have a companion, others probably can too. Since that first discovery, astronomers have found more planets and planetary mass objects around brown dwarfs. Not many brown dwarfs are faint, and their planets are even fainter, making detection incredibly difficult. But enough to establish a pattern. Brown dwarfs can form disks during their early evolution, just like stars do. And in those disks, planets can form. Research shows that the disks around brown dwarfs are smaller and less massive than the disks around stars. A brown dwarf doesn't gather as much material during its formation, so there's less leftover material to form a disk. And the disk itself is cooler because the brown dwarf doesn't heat it as much. But the basic process is the same. Dust grains collide and stick together, growing into pebbles boulders, planetesimals. Over time, these planetesimals accumulate into larger bodies. If there's enough material, a planet forms. But the planets that form around brown dwarfs are different from the planets around stars. For one thing, they're likely to be smaller. There's less material available, so massive gas giants like Jupiter are less common. Rocky planets or small ice giants are more likely. And they orbit closer to the brown dwarf than planets typically orbit stars because the disk is smaller and the gravitational influence of the brown dwarf extends over a shorter range. This has implications for habitability. Habitability is the idea that a planet might have conditions suitable for life, liquid water, on the surface being the key criterion. For a planet orbiting a star like the Sun, the habitable zone, the region where temperatures allow liquid water, is relatively far out. Earth sits comfortably in the Sun's habitable zone. Mars is on the outer edge. Venus is too close, too hot. But for a brown dwarf, the habitable zone is much closer and much narrower. Brown dwarfs are cool, and they're cooling over time. Early on, when a brown dwarf is still warm from its formation, there might be a brief window where a planet at the right distance could have liquid water. But that window closes as the brown dwarf cools. After a few 100 million years, the brown dwarf is too cool to keep any planet warm enough for liquid water, unless the planet has some other heat source like tidal heating from gravitational interactions. And even in that early warm phase, the habitable zone is incredibly close to the brown dwarf. For a young brown dwarf at 2000, Kelvin, the habitable zone, might be only a few million kilometers away, closer than Mercury is to the Sun. A planet orbiting that close would be tidally locked one side, always facing the brown dwarf, the other side in perpetual darkness. The temperature difference between day and night would be extreme. Winds would howl from the hot side to the cold side, trying to equalize the temperature. It would be a harsh, challenging environment, but not impossible. Scientists studying extreme environments on Earth have found life in places that were once thought uninhabitable. Deep-sea hydrothermal vents, acidic hot springs, frozen Antarctic lakes. Life adapts. If there's liquid water and a source of energy, life might find a way. So, a planet in the habitable zone of a young brown dwarf, as unlikely and unstable as that zone is, can't be ruled out as a potential home for life. There's another possibility, one that's even more speculative but intriguing. What if life doesn't need a planet at all? What if it could exist in the atmosphere of a brown dwarf itself? This idea isn't new. Carl Sagan speculated about it in the 1970s when he was studying Jupiter. He imagined that Jupiter's atmosphere, with its complex chemistry, its energy from internal heat, its layers of different temperatures and pressures, might host life. Not life as we know it, not organisms with cells and DNA, but something different. Floating organisms, perhaps, that metabolize hydrogen and methane, that drift in the atmospheric currents that reproduce and evolve in the sky. Sagan's idea was never proven. We've sent probes to Jupiter and they've found no evidence of life. But the concept remains valid. An atmosphere is a medium, a place where chemistry happens, where energy flows. If the right conditions exist, life might emerge. And brown dwarfs have atmospheres, thick ones, with chemistry even more complex than Jupiter's. Consider a warm brown dwarf, an L-type at 1500 Kelvin. Its atmosphere has layers. Near the photosphere, silicate clouds form. Deeper down, the temperature rises and different materials condense. Water vapor is present. Carbon monoxide, methane, ammonia. There's convection moving material up and down, mixing chemicals, creating gradients. There's energy from the heat of the brown dwarfs, cooling from the decay of radioactive elements, if any are present. Could life exist there? Could some kind of organism, maybe a chemical system that self-replicates and evolves, survive in that environment? The gravity would be crushing dozens of times Earth's gravity. The pressure would be immense. The atmosphere would be toxic to any Earth organism. But life doesn't have to be like Earth life. It just has to follow the same basic principles. Replication, metabolism. Evolution. No one has found evidence of life in a brown dwarf atmosphere. We don't even know what to look for. But the possibility exists in theory, and it's a reminder that life might be more versatile, more adaptable than we imagine. If it can exist in Earth's deep oceans, in boiling hot springs, in frozen deserts, why not in the atmosphere of a brown dwarf? Why not in places we've barely begun to explore? Of course, the more immediate question is whether planets around brown dwarfs could be detected at all. As we've mentioned, it's difficult. Brown dwarfs are faint, and planets are fainter still. Most of the techniques we use to find exoplanets rely on the planet's effect on its host star. The radial velocity method measures the wobble a planet causes in its star's motion. The transit method measures the dip in brightness when a planet passes in front of the star. But brown dwarfs are so dim that these methods are challenging to apply. Direct imaging, the method used to find 2M1211b, works better for brown dwarfs because the contrast ratio is more favorable. A planet might be 1,000 times fainter than a star, but only 10 or 20 times fainter than a brown dwarf. So, if the planet is far enough from the brown dwarf, and if it's still warm from its formation, it can be directly imaged. But only a few planets have been found this way. Most planets around brown dwarfs, if they exist, remain hidden. Gravitational microlensing is another technique that might work. When a brown dwarf passes in front of a more distant star, its gravity bends the star's light, causing a brief brightening. If the brown dwarf has a planet, the planet's gravity adds a second smaller brightening. By analyzing the light curve, astronomers can detect both the brown dwarf and its planet. This method doesn't require the planet to be bright or close. It just requires the right alignment, a rare event, but one that happens often enough in large surveys. And then there's the possibility of moons. If brown dwarfs can have planets, can those planets have moons? And could a moon orbiting a planet orbiting a brown dwarf be habitable? It sounds absurd, layers upon layers of orbital complexity, but the physics allows it. Jupiter has moons, some with subsurface oceans. Saturn's moon. Enceladus has geysers of water erupting from its south pole. These moons are kept warm by tidal heating, the gravitational pull of their planet, flexing their interiors, generating heat through friction. A moon orbiting a planet around a brown dwarf could experience the same tidal heating. The brown dwarf's gravity, the planet's gravity, and the moon's own rotation could create tidal forces that warm the moon's interior. If the moon is large enough, and if the tidal heating is strong enough, it could have liquid water, possibly even a thick atmosphere. It's speculative, yes, but not impossible. And if such a moon exists, it might be one of the strangest habitable environments in the galaxy, a world warmed not by a sun, but by the gravitational dance of its parent bodies orbiting in the faint glow of a brown dwarf that never became a star. What would it be like to stand on such a world? The sky would be dark, almost black, lit only by the dim infrared glow of the brown dwarf invisible to human eyes. If the moon had an atmosphere, you might see aurorae shimmering curtains of light, caused by charged particles interacting with the magnetic field. You might see the planet itself looming large in the sky, reflecting the faint light of the brown dwarf. And in the distance, countless stars brighter and sharper than we ever see from Earth, because there's no bright sun to wash them out. It would be a world of darkness and cold, warmed only from within, lit only by the faint glow of distant objects. A world that exists on the margins in the places we didn't think to look. And yet, it would be a world with its own geology, its own atmosphere, maybe even its own life. We don't know if such worlds exist. We've barely begun to search. But the fact that we can imagine them, that the physics allows them, is enough to make us wonder, to make us question our assumptions about where planets can be, where life can exist, where habitability ends and impossibility begins. Brown dwarfs in their quiet cooling might be host to entire systems. Planets, moons, rings, perhaps even comets and asteroids. Miniature solar systems, faint and hidden, but real. And as our technology improves, as our telescopes become more sensitive, we'll find more of them. We'll map their orbits, measure their atmospheres, search for signs of water, of chemistry, of anything that hints at complexity. And maybe we'll find something unexpected. Not just a planet, but a living world. Not around a star, but around a failed star, an object that almost was, but never quite became. Because if there's one thing we've learned from studying the universe, it's that life finds a way. It exists in the most unlikely places. And the margins, the in-between spaces, the forgotten corners, those are often where the most interesting discoveries await, reminding us that the cosmos holds more wonder than we've yet dreamed of, and more stories than we've yet told, which brings us at last to the final question, the one that ties all of this together. What does it mean to be a brown dwarf? We've traveled through their formation, watched them cool across billions of years, explored their storms and clouds, discovered their coldest examples, imagined the worlds that might orbit them. We've traced their existence from birth in collapsing gas clouds to the long, patient fade into darkness. And through it all, one question has lingered beneath the surface, a question that's not really about brown dwarfs at all, but about us, about how we understand the universe, about how we define success and failure, light and darkness, being and becoming. Because when we call brown dwarfs failed stars, what are we really saying? That they tried and didn't make it, that they fell short of some cosmic standard, that their existence is defined by what they're not, rather than what they are. It's a human impulse, this need to categorize, to measure everything against an ideal. We do it with people, with careers, with dreams. We look at what could have been and call the reality a failure. But the universe doesn't think in those terms. The universe doesn't judge. It doesn't measure brown dwarfs against the standard of the sun and find them wanting. It simply creates what the laws of physics allow. A cloud collapses. If it gathers enough mass, fusion begins and a star is born. If it doesn't, a brown dwarf forms instead. Both outcomes are natural. Both are complete in their own way. So, maybe the real lesson of brown dwarfs isn't about failure at all. Maybe it's about acceptance. About existing fully in whatever form you take without apology, without comparison. A brown dwarf doesn't wish it were a star. It doesn't spend billions of years regretting the mass it never gathered, the fusion it never achieved. It simply is. It glows with whatever light it has. It cools at its own pace. It exists in the margins, yes, but existence in the margins is still existence. And those margins, as we've discovered, are far more populated than we ever imagined. Scientists estimate there could be between 25 billion and 100 billion brown dwarfs in the Milky Way galaxy alone. 25 to 100 billion. That's roughly one brown dwarf for every few stars. An invisible population outnumbering many types of stars, filling the spaces between the bright points we see when we look up at night. Think about that for a moment. The galaxy we thought we knew. The galaxy of stars and planets and nebulae has been hiding this entire other population. Brown dwarfs have been there all along, cooling quietly, glowing faintly, waiting for us to develop the technology to see them. And now that we can see them, we're realizing they're not rare oddities. They're a fundamental part of the galaxy's structure, part of the census of objects that make up the Milky Way. They contribute to the galaxy's mass, to its gravitational landscape. They influence the motion of nearby stars. Some of them have planets, possibly habitable moons, maybe even life. They're laboratories for studying atmospheric physics, planetary science, the behavior of matter under extreme conditions. They're time capsules, some of them nearly as old as the galaxy itself, carrying information about how the Milky Way evolved, how stars and planets formed in different eras. Brown dwarfs are not footnotes. They're chapters, important ones. And here's something that should give us pause. For most of human history, we didn't know they existed. We looked up at the night sky, mapped the stars, built telescopes, studied the cosmos, and we missed them entirely. Not because we weren't looking carefully enough, but because we didn't have the right tools. We couldn't see infrared light. We couldn't detect objects that dim, that cool, that subtle. So, what else are we missing? What other populations of objects are out there invisible to our current technology, waiting for the next breakthrough? What will future astronomers discover that will make our current understanding look incomplete? The universe has surprised us before. Dark matter, dark energy, exoplanets, gravitational waves. Each discovery revealed something we didn't know. Brown dwarfs are part of that pattern. They're a reminder that the cosmos is deeper, stranger, more complex than any model we build. And that's okay. That's the beauty of science. We don't need to know everything. We just need to keep looking, keep asking questions, keep refining our tools and our understanding. Each answer leads to new questions. Each discovery opens new territories to explore. Brown dwarfs were a mystery for 30 years, from prediction to confirmation. Now, they're a field of study, with thousands of examples, detailed spectra, atmospheric models. But we're still learning. We still don't understand everything about how they form, how their atmospheres work, what happens to them over trillions of years. There are brown dwarfs we haven't found yet, closer than any known star drifting invisibly through space. There are planets around brown dwarfs. We haven't detected worlds with their own stories, their own potential. There are atmospheric phenomena. We haven't observed chemistry, we haven't measured physics, we haven't tested. Brown dwarfs are still teaching us, and they will continue to teach us for as long as we're willing to listen. But beyond the science, beyond the data and the models and the discoveries, there's something else. Something about the existence of brown dwarfs that resonates on a deeper level. They're objects that almost were something else. Their potential that didn't quite manifest. Their dreams that didn't come true, at least not in the way we expected. And yet they exist, fully, completely. They have mass structure complexity. They have atmospheres with clouds and storms. They emit light, faint but real. They cool over time scales that dwarf civilizations. They might host planets, might harbor life, might be home to worlds we can't yet imagine. They're not less than stars. They're different from stars. And that difference is what makes them beautiful. There's a human story in that. We all carry unrealized potential, things we wanted to be but never became, paths we didn't take, dreams that faded. And it's easy to define ourselves by those absences, to look at what we're not and feel like we fell short. But what if we're more like brown dwarfs than we think? What if we're complete as we are glowing, with whatever light we have, existing in our own unique way, not failing to be something else, but succeeding at being ourselves? Brown dwarfs don't need to burn to matter. They don't need to shine like the sun to be significant. They exist in the in-between, in the margins, in the quiet spaces. And they're enough. They've always been enough. Maybe we can carry that lesson with us. Not just about astronomy, not just about objects in space, but about existence itself. That not everything needs to be bright to be beautiful. Not everything needs to burn to be warm. Some things glow softly, patiently in the dark. And those things, the quiet things, the subtle things, the things that exist without fanfare, they last. They endure. Brown dwarfs will outlast the sun. They'll outlast most stars. They'll be here cooling, fading, but still here long after the bright lights have gone out. There's a kind of quiet victory in that. Not the victory of conquest or dominance, but the victory of persistence, of being, of lasting, not because you burned brightest, but because you never needed to. And in the far future, trillions of years from now, when the last stars have exhausted their fuel and the universe is dark and cold, brown dwarfs will still be there. Frozen spheres of hydrogen and helium, no longer glowing, no longer warm, but still massive, still real, still witnesses to everything that came before. They'll be the universe's memory, the last remnants of an age when stars burned and planets formed and life maybe flourished in the warmth. They'll be silent then, but they'll still be there. And maybe that's all any of us can hope for. To exist fully for as long as the laws of nature allow. To be present, to be real, to be ourselves, without needing to be anything more. The stars that never fully awoke. That's what we called them. But maybe they were awake all along, just in a different way, just in a quieter way, just in a way that took us 3 decades to notice and that we're still learning to understand. So, as we drift back from this journey, as we return from the cold edges of the galaxy to the warmth of this moment here now together, let's carry that understanding with us, that the universe is full of things we almost missed. That beauty lives in the margins. That not everything that matters shines bright. That some stories are told in whispers, not shouts. And that the quiet things, the patient things, the things that glow softly in the dark, they're worthy of our attention, our wonder, our respect. Brown dwarfs have been cooling for billions of years. They'll cool for billions more. They're not in a hurry. They've taught us patience, complexity, humility. They've expanded our understanding of what's possible, what's common, what exists in the spaces we thought were empty. And they're still out there, right now, drifting through the galaxy, glowing faintly in infrared, hosting worlds we haven't found, carrying stories we haven't heard, waiting patiently for us to look a little closer, to ask better questions, to develop better tools, waiting to teach us something new. The universe is vast, but it's also gentle. It makes room for the things that almost were. It holds space for the in-between. And so do we. Thank you for drifting with me through this quiet corner of the cosmos. Thank you for listening to the story of brown dwarfs, the stars that never fully awoke, but that glow nonetheless, softly, patiently in the dark. There are more stories waiting, more mysteries to explore, more whispers from the universe ready to be heard. And when you're ready, when the night is quiet again, we'll meet here once more and let curiosity guide us somewhere new. Until then, sleep well, dream gently, and remember that not all light needs to shout to be seen. Some of the most beautiful things in the universe glow quietly, waiting for those patient enough to notice. Good night.